All right, here's the quick video trying to explain effect size. So every statistical test has three things to look for. Number one, is it significant? Number two is what is the effect size? Number three, what is the power? So we're talking about effect size, and that basically translates to what percent of the variance of the dV can you explain by your different groups? Okay, that's the kind of test you're using. So we're going to do a quick example. So we're going to look for the reasons of why the variance is the way it is in a group of data. Okay, so the variance of the total number of push-ups. So let's pretend we had 200 people, and we made them do push-ups for a minute, and we recorded them, and we have their push-ups right here. Blah, 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 blah. And pretend you got 200 of the scores here, and they're just all over the place. So that all over the place, that spread of the number of push-ups is what we call variance. And we want to be able to explain why some people do a lot of push-ups and why some people don't do so many push-ups, right? Again, there's that variance question. And again, we're trying to explain why the variance is the way it is here. So we're going to try to do some grouping. You know, maybe the different groups is a good reason why we're getting such weird numbers up here. And if we had one group that were Girl Scouts and a second groups that were Navy SEALs, that's obvious here, right? That would explain the low numbers. The Girl Scouts would be getting the low numbers. The Navy SEALs would be getting the high numbers. So with something like that, it's grouping that's causing the variance in the number of push-ups. And for this example, you would have a huge effect size, a very large effect size. In other words, the grouping can explain most of the variance in the number of push-ups that these guys can do. That's what this circle means. So if the red circle was the total variance, the grouping factor can explain most of it, right? Large effect size. So now let's go look at your stuff. And you have to hand calculate the effect size, and that little n is eta squared. That's the type of effect size. There's several different types of effect size. There's eta squared, omega squared, r squared, Cohen's d. The list goes on and on and on. But for this test, we're using eta squared, and this is how you calculate it. The z-score was from the SPSS output divided by 1 less than the sample size. So I took this very first one, scale 7, HS. The effect size was 0.043. So there's the scale, right? It's HS. And the effect size was 0.043, which means that your grouping can explain about this much of the variance. Not very much, around 4.3% of the variance. So that brings up a big question. You know, is the variance coming from the grouping? Because, you know, according to the chart, that's between weak and a medium effect size. You know, it's not real weak, but it's not the strongest in the world. But again, with such a small effect size, the variance between the scores might not be because of the way you're grouping them. That's what effect size is all about. And here they are right here. Let's take a scroll down the effect size lane. So most of yours are between 0.01 and 0.06, which is 0.01 is small, 0.06 is medium, and large is 0.14. And there's another medium. This is probably the biggest one you got right here, which is scale 32. So that's basically what it means. And again, that's why this is the first time I've ever actually calculated effect size for a non-parametric test. Non-parametric tests are well known not to be a very strong test. They're not as strong as their parametric counterparts. So that's why right off the bat, I knew you were going to get some real low values for the effect size. But I hope this explains this to you. All right, I'm going home. I'll be back on Monday. Stay cool. MGZ out.